Okay, in this video we're going to talk a little bit about file data and file data formats. So I have a Linux terminal open here and I am on my desktop, and I can create a file using the touch command, and we can call this hello. And notice I don't have to have a file extension here. I just name the file hello with no file extension. So the information we can put inside of a file is rather arbitrary. It's arbitrary data. More often than not, we're going to be making text files. So text files seem like the most appropriate thing to start with when we're discussing file data. Okay, so if I look at this file, I can use the ls command, ls-l, and list out some information. I have another PNG file in this directory, and this is the file I just created called hello, and has size 0 right now. All right, so if I open this file up, I can open it with Nano, or I can use my text editor here, Atom. I can type in characters. Right? I can type in things hello with a capital H and an exclamation point. All right, so how is this information stored? Right? I can close the file and reopen it, and there it is again. So this has to be maintained somewhere. This data is stored somewhere on the system. Same from the file system. I can use from the terminal, I can use the cat command to see what's inside of my file called hello, and there's that text again, right? So we know this data is persisting somewhere. So where does it live, and how is it stored? So well, we've heard that computers speak binary, right? They talk in ones and zeros. Well, effectively, all of this data has to, in one form or another, eventually turn into binary data so that the computer can understand it and store it, right? Not necessarily understand it, but process it, right? So to store this data as ones and zeros, we need some sort of system or a protocol or a code, right? So this is where the ASCII code comes in. Okay, so I'm at ASCIItable.com, and ASCII stands for American Standard Code for Information Interchange. Okay, so that's ASCII, A-S-C-I-I. Basically what this is a translation between the numeric value and a character. So some character on our keyboard, for example. So here we see a listing from the decimal numbers 0 all the way up to 127. Okay, so there, if you include 0, that's 128 characters that can be encoded with this ASCII code. Right? So the ASCII code, again, is a number and an associated character. Right? So it's just a mapping. I'm mapping between some number and a character, or a character to the number. Right? But it's just a protocol. It's a standard. It's something we've invented. It's an agreed upon standard. So if I'm storing something in a file, I can use any standard I want. You know, I don't have to use ASCII encoding. I could make up my own encoding. I could say the number 0 is the letter capital A, and I could say the number 1 is capital B. I could do that, right? But the system that we've created as computer scientists and the computing community at large initially agreed upon the ASCII. At least the Americans did, the American Standard Code for Information Interchange. Okay. So this gives us a starting point of how this data might be stored in our file. All right, so the letter H, for example, we can look up on our ASCII table, and that should be the decimal number 72. And then we would see in hexadecimal, that same data can be represented as 48, right? And the character right there. So the characters you can kind of think of as just images. They're commonly called glyphs. They are just a picture of a representation of what humans see as the character H. But in terms of how the computer stores this information and understands it, you know, if you want to use that word, understands, it's just ones and zeros. All right, so we can use a special command from the terminal to kind of examine the contents of our file in a more raw form. Right? So we see the cat command basically just outputs the contents of a file, but it's doing something else too, because we know that file is binary data. So the cat command makes the assumption that the data in this file is text data, and it makes the assumption that it's ASCII, right? And so when it sees a series of ones and zeros, that represents the letter H, it replaces the ones and zeros and displays this character. Okay? So then the next chunk of ones and zeros it sees, what is the value of that? What numeric value? And then it looks up that numeric value in the ASCII table, and we see it's the E character, so it displays that picture of E, right? And so that's all it's doing. It's taking chunks of ones and zeros and translating them from their numeric value using this ASCII chart, and then it posts the picture related to that numeric value. All right. So one thing that we need to mention here too about ASCII is, why are there 127 characters? Okay, so it was 128 if you include the number 0. And these first 32 entries in the ASCII table are actually control characters. They're not things you would normally see. Most of the time we're not aware of these actually even being characters, with a few exceptions. Starting at 32, these are like our keyboard characters. These are things that we can actually see, right? Most of these we can't see. There are some exceptions. The tab character, when you press tab on your keyboard, that's actually represented as a single character. But the terminal and different applications know that when you have a tab character, you actually want additional space. Okay, so tabs are usually 4 to 8 spaces, but they're actually stored in the file as one character. Right here we have a line feed character, or a new line. A new line is what tells the computer when you're reading a file, to move to the next line. Right? I can open my file hello, and underneath here I could say, oh, you are great. It's a nice positive message, right? But see, in between these two lines, there's actually a character stored here that's called a new line character, and that's what tells the terminal to go to the next line. So that's how this is stored on disk. How else would the terminal know that after the exclamation point we're supposed to start a new line? Well, there's just a character, just like any other character. All right, so we can save this, exit, we use the cat command, and look at what's inside here. Hello, and we see again, even the cat command recognizes that new line character, and that means, oh, okay, we got to go to a new line and print this stuff out. All right, so we have from 0 to 127, right? That is 128 different characters we can represent. So I'm going to open up Python in interactive mode just so we can use it as a little bit of a calculator. Why is 128 significant? Well, it's a power of 2. So how many things can we represent in one bit of information? Well, a bit is a binary digit. It's either a 0, so that's one thing, or it's a 1, and that's another thing. Right? So that's 2 options to the first power. There's 1 digit, 1 bit. So we can hold 2 different things in 1 bit of information, right? That seems fairly obvious. What if we have 2 bits of information? Well, I can have 0, 0, I can have 0, 1, I can have 1, 0, and I can have 1, 1. Right? So that's 4 different things. So that's binary, base 2, and we have 2 bits. 2 bits of information, so that's squared. So that's a total of 4 things. If I have 3 bits of information, that's 2 to the 3rd. So there I can store 8 different values in 3 bits. What about 4 bits? 16. And 5 bits, 32. 6 bits, 64. And 70, or 7 bits. This is where we get to our interesting number, 128. Okay, so that means with 7 different bits, 7 ones and zeros consecutively, I can map all of those numbers to one of these special characters. Okay, so hopefully we're familiar with the idea of a bit and a byte. A bit is 1 binary digit, right? And it takes 7 bits here, right, to give us 128 possible values. and those values can be mapped to characters using the ASCII code, right? A byte is 8 bits, not 7 bits. So with a byte of information, we can store all of these ASCII codes and we'll have one extra bit. Okay? So the assumption is if we have a byte of information and one byte of information represents one of these characters, that extra bit is at the very beginning and it's a 0. All right? So that would basically keeps the number the same. Right, so if I have in decimal, if I have the number 7, it doesn't matter if I have a 0 in front, that's still the number 7. So that's all we're doing. We have some 1s and 0s, and 1, 2, 3, 4, 5, 6, and let's say there's 7 bits of information. So that could technically represent a ASCII value over here. But if I wanted to make that an even byte, which would be 8 bits, then just add a 0 at the beginning. Right, it doesn't change the value of the number. But it does go ahead and complete my 7 bits and turn it into 8 bits or 1 byte. Okay, so bytes are kind of a standard size of data that we use in computer science. So keep in mind for now that we just have this extra bit and it's just normally a 0 when we're talking about ASCII, right? But the actual number is 7 bits here. All right, so we can translate this and see what value this would be associated with. So I just picked a number here. I'm not sure what this is going to be, but I've created this chart. So binary numbers to hexadecimal, right? So the binary number 0 is 4 bits, right? And that's associated with 0 in decimal. This is 1. This is 2 in binary. 3, 4, 5, 6, 7, 8, right? And we go all the way down. Once we get to 10, this gets a little bit interesting, right? Decimal does not have a single digit character to represent 10. So, like any number system, we add a 1 to the left-hand side and restart our digits again at 0, right? Hexadecimal, however, is base 16, right? Binary is base 2, decimal is base 10, and hexadecimal is base 16. So in base 16, we do have a character to represent the value of 10, a single digit, A. And 11 then is B, C, D, E, and F. So there are 16 characters, 16 symbols in the hexadecimal alphabet, right? There are 10 symbols, 0 through 9, in the decimal alphabet. And there are 2 symbols, 0, 1, in the binary alphabet. Right? But there's this really nice relationship between binary and hexadecimal. So for any 4 bits of binary, how many different things can we store? How many different numbers? Well, using, let me just ignore that for a minute. Using our formula that we used before, base 2 and raised to the number of digits. So there's 4 digits. So how many possibilities can we make? How many ways can we number things? So with 4 bits of information, we can have 16 different possibilities, right? And we see here, these are all the different ways you can have 1s and 0s, 4 bits of 1s and 0s, and there are 16 of them. And so there is a nice, perfect one-to-one mapping for each 4-bit value. There's an associated hexadecimal value, right? So 0011 maps to hexadecimal value 3. Right? So if I want to represent something like this number up here in hexadecimal, since there is a one-to-one mapping of every 4 bits, I can take these 4 bits, look at 0101 and look that up in my chart. 0101 is 5, and so the next 4 bits over here is 0110. 0110 is 6. So this is a 6 and then a 5 in hexadecimal. Okay, so anytime you see 2 hexadecimal digits, you can represent 1 byte of data with 2 hexadecimal digits. So 1 byte is 8 bits, and a byte is also 2 hexadecimal digits. All right, so this was a 6-5 in hex. So let's go back to our ASCII table, and look up a 6-5. So here, HX, we're looking for something that starts with a 6 and a 5, and there it is. 6-5 is the letter E in hexadecimal. It's 6-5 according to the ASCII table, right? So this 65 value is 101 in decimal, right? These two numbers have the same quantity, right? Just like this number in binary, this is the same quantity. This is 101 in decimal, right? Or the number 65 in hexadecimal. It's still the same number of items, right? And that number, no matter how you represent it, no matter what number system you use, if you use the ASCII table, you can convert that to the letter E. Right? So the way this kind of works, I'm going to copy that and exit out of Python real quick. If I use the cat command and look at hello again, each one of these characters we're storing in a byte. Right? So the H is 1 byte of information, and remember we have the 0 at the beginning. And then we have another 8 bits, which is a byte of information. We have the 0 at the beginning, and then we have our 1s and 0s. Right? So if I open up a new file here, these are the 1s and 0s that represented the letter E. We just saw that. Right? So this was 65 in hexadecimal and 101 in decimal, and in ASCII that's the letter E. All right? So there is a command line tool that will help you look at data in a file as binary. Well, actually, technically as hexadecimal. So the command is called Hex Dump, right? And if we use the -C option, it's going to look at the data 1 byte at a time as it's stored on the disk, and it's going to try to convert it to a character if it can, but it'll show us the hexadecimal value. So Hex Dump -C, and we want to look inside of our file hello. Okay, so this beginning part, this is the number of the starting position, the byte number. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? And these are in hexadecimal, right? So there were 16 bytes on this line, and so this is starting at byte 16. This is byte 0, 1, 2, 3, 4, 5, right? All the way up to this is byte 15. And this is just labeling it. This is saying, okay, we're starting at byte 16. So remember, in hexadecimal, this position is the 16's place, right? In decimal, that's the 10's place, and in binary, that's the 2's place. So this number is hexadecimal, and it's the 16's place. So here we see we have this many bytes of information, right? So this is 16 bytes plus 6. Right, it should be 22. So 16, 17, 18, 19, 20, and 21, right? And if you count 0, that's 22. And then over here on this side, it's trying to convert each one of these bytes. So this is the byte 48, right, which we know we can translate one hexadecimal digit to binary. So that would be 4 bits. And then 4 bits. So that would be 8 total bits. These 2 hexadecimal digits is going to be 8 bits. That number can be translated using ASCII to the capital letter H. And here is our byte of 65, right? We have this byte 65, and we said that is the letter E. Well, according to this, here is our letter E. So we've technically stored a byte of information as 1s and 0s. Hex Dump converts it to hexadecimal because it's shorter to store. Imagine if every 2 digits here was 8, this entire line would be really wide, right? So this gives us a more condensed version of looking at numbers in binary. So that's why hexadecimal is used. It's just a more condensed version of looking at things in binary. All right, but we see each one of these bytes represents a character, and we can guess here 6C is the character L. Not only because we sort of know that already that that's how that works, but here we see 6C and then 6C. The duplication is a hint that we have two of the same thing, two characters, right? So that should be O, and then the 21 should be the exclamation point. So we can verify all this. We can open up our ASCII table and look at the character exclamation point, and sure enough, in hexadecimal, that's the number 21, 21. Right? So this is nice. We can see that the data is actually stored in a binary form. Right? And notice after the hello character, the exclamation point, right, we have this 0A character, right? And over here on the right, it just represents it as a dot, because there's no good way to represent the new line character, right? If we look at 0A, right, the hexadecimal, so 0, there's an implied 0 at the beginning, and A. So that's our line feed. That's the new line character, right? So 0A is a new line, and the Hex Dump command is trying to print out, if it recognizes it as an ASCII character, it's trying to print it out. But there's no good way to print out a new line character other than going to a new line, which we can't really do in this chart format. So it just puts a dot. Whenever it sees something it doesn't know how to deal with, it puts a dot. So here at the end we have another character that's a new line character at the very end of our file, and it just puts a dot there. Right? So this is how text files are stored. Text files are stored as bytes of information, and this is actually an early standard. The ASCII system is one of the first codes that was created, and it's the American Standard Code of Information Interchange. Again, American, right? We don't see any other any languages here, right? There, you can imagine there's lots and lots of different characters and different languages that would eventually need to be supported by some sort of binary system. And there are many different types of text encodings. This was just one of the first and one of the simplest. And so it's easy to describe where one byte of information is represents one character in this ASCII table. All right. So what about other types of data? So here, this image we were looking at before, this is just a PNG image, right? And it's binary data. It has to store the data for a number of different pixel colors, right? And in a grid system. So this is some data format that's in binary, right? So these values here, the B, or the, all of this, these are actually just pixels. So these aren't stored the same way. These aren't stored in ASCII, right? So if I look at this PNG, we know that PNGs are pictures. They can be of anything. It could be stored at a picture of a sunset, right? Obviously there's no ASCII representation of a sunset, right? So this has to be stored in a different way. And the way this kind of works is every pixel has a certain color, so it stores the pixel and then the color value associated with it. And ping's a little bit more complicated because it does compression and different things like that to make the image size smaller. But you can imagine you would store for every single pixel data about the color of that pixel and then the size of the image, the dimensions of the image, so you could line out the pixels and know when to stop and start with the next row of pixels and go to the next row, right? So we can look at this image file using Hex Dump, and we can actually see the binary data. So if we look at Hex Dump, and we can use -C again, and we're going to look at our image file, we see this is pretty big. As we scroll up here, this is a large binary file. Quite a lot of information here. Now as I scroll up to the top, we can take a look at this and we notice a few things. All right. First, we have bytes of information, just like we did with our text file. But over here on the right, when the Hex Dump program is trying to look at basically random data of ones and zeros, and when occasionally one happens to match an ASCII character, it prints it out, right? But that's not necessarily meant to be an ASCII character. This is just the Hex Dump program seeing a number and saying, oh, I'm going to try to make that an ASCII character. And it does, but that's not what this data is supposed to mean. This data is supposed to be pixel data. This is supposed to be about the color of a dot on the monitor, right? And so what the Hex Dump command is doing here is forcing a code or a translation onto data that was not designed to work with that code. And that's why it looks like gibberish, right? Because you can do it, but it doesn't make any sense. So that's why protocols are important. If I give you a big blob of data like this, if you assume it's ASCII, then you're going to make this translation and it's going to be wrong, right? So the type of data we're dealing with is important, right? Otherwise it's just going to look like gibberish. Now, one thing to note also here at the beginning is we do have some stuff that does seem to make a little bit of sense, right, as far as ASCII is concerned. So .png, this is a PNG file, so that seems like that would be wildly coincidental, right, if that wasn't actually designed to be an ASCII character, or a set of ASCII characters. So it turns out the PNG protocol does define a few ASCII characters, and here we see some other stuff that it would be wildly coincidental to have something that would be, you know, English readable based on random bytes of data, right? So this is text software genome screenshot. So this information here is also ASCII. So within the protocol of the PNG data format, there are sections of it, right? Divisions of the bits that are designed specifically to hold character data, right? But then there are other sections that are not designed. So that is the file format protocol. And whatever file format you're dealing with kind of defines what that protocol is. So PNG is an image format, and it has, you know, different sections of these bytes represent different things, right? And so that depends on your data format, how that's all divided up and organized. And so one of the things we do to convey a file's data format is we use an extension. So we use the .png file extension, right? But this is just part of the file name, and this can be changed, and it will still be PNG file data, right? So you can't always rely on the extension, but the idea is we use the extensions to help us remind us what kind of data is inside of this file. All right. So that's an example of a couple of different data formats that you can use, well, that you can look at least, and this gives you a sense of how the computer looks at this data, right? When we see this data, we are running this data through a filter. We're running this through a computer program that's filtering out this data and making sense of it and translating it to the thing that we see here. Each one of these little tiny pixels, right, might be a blob of data like this. That might be a pixel, right? You know, maybe that's a pixel. So this is all being translated by way of a computer program, and then it tells the computer processor to communicate with your display to make one pixel one color, and then the next pixel the next color. And it all does this incredibly fast, right? And it has to refresh the screen over and over and over. But this is how the data is stored on the disk, as ones and zeros, right? And this is the hexadecimal version of ones and zeros. So that's a little bit about file data and file types. One thing to also consider, the file data here, right? We see when we're looking in the file, this is what's associated with that file data, these ones and zeros. Nowhere in this file data do we see the name of our file, right? We don't see binhex.png. The PNG protocol does include .png at the beginning, but that's not related to the file name. I can remove the file extension and this will still be there, right? And so hello isn't in here. This is the text that we added, right? But the name of our file is not included in the file data. So one thing that's important to get out of this is that the file data is separate from the file name and also information about the file, right? We can use the ls command and we can look at ls-l, and we have additional information about this file, the permissions, who owns it, dates, that sort of thing. All of this is not in the file either, right? Because we just looked with Hex Dump and we saw what exactly is in our file, and it's these bytes, all of these bytes, 4865, right? So the file data is separate than the information about the file. The information or data about the file is called metadata, right? The file itself is this data, and then the metadata is information about that data. So like the name, right? That might be metadata. The access times, the permissions, that's metadata. That's data about the actual data. Okay? So if you hear the term metadata, that's very important. It's just data about data. All right, rather abstract concept. Okay, so this has been a little video on file data and data types.